In the last lecture, I had introduced the concept of a unit cell in a 3D lattice, and as you can see here pictorially. So, a 3D lattice unit cell in general can be called as a parallel piped, and this is a general unit cell. It has 6 lattice parameters A, B and C, alpha, beta and gamma, as can be seen from the figure. Now, we need to populate this parallel piped with lattice points. So, where can I put the lattice points, so that I have translation symmetry in the lattice? So, one of the place I can put the lattice points are at the corners. So, this is an example of a unit cell with lattice points only at the corners of the cell. Hence, this is a primitive unit cell, since it will have effectively one lattice point per unit cell. Now, in addition to these lattice points at the corners, I can also add a lattice point in the center of this cell, called the body centered position, as shown here with a light colored dot that is shown here. And one thing I must emphasize again, that the lattice points are shown rather as bigger, somewhat bigger circles, so that they are visible, but they should not be confused with atoms. So, this distinction between the lattice point and the atoms have to be always to be kept in mind. So, here I have lattice points at corners plus a lattice point at the body centered position, and you will also note that the first cell, which is the primitive cell, the symbol that will be used for all primitive cells is P. Similarly, for the body centered cell, where I have lattice points at the corners and a lattice point in the body centered position, the symbol that is used is I. Similarly, I can, instead of adding a lattice point at the body centered position, I can add 2 lattice points at 2 opposite faces of this parallel pipe. So, now I have lattice points at the corners plus 2 lattice points, one at the top face and other at the bottom face, and such a cell is actually called a base centered or an end centered cell, and the symbol that we use could be either A, B or C, depending on which of the 2 faces I have chosen. For example, in this particular figure, I have chosen the C face, because the C face is parallel to the A and B axis, and the C axis comes out of the top face or the bottom face. So, that face is called as the C face. So, this face out here is the C face. Now, why I am using 3 possible symbols A, B or C? Well, I can put lattice points on the C face, but I can also put lattice points on the A face. A face would be the front face and the rear face. Similarly, I can put 2 lattice points on the B face, which is the left face and the right face. So, depending on where I put these 2 lattice points, the symbol I will use would be A, B or C. A fourth possibility is lattice points at the corners and the lattice points in the centers of all the 6 faces. Such a cell is called as a face centered cell, and the symbol that is used is F. So, in this way I have 4 possible lattices that I can get out of a parallel pipe. Now, the next question that we have to address is, what should be this parallel piped cell look like? So, there is a set of what are called as conventional cells, which I am sure all of you would have come across in any basic course on material science, and there are 7 different parallel pipes which are conventional parallel piped, which have some specific, and they are described by some specific relationships between A, B, C and alpha, beta, gamma. So, let us consider this, and those 7 cells are called crystal systems. Now, here are the 7 crystal systems: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. Now, this is a commonly used definition you will find in most books where the axial and the angular relationships, that is the relationship between the parameters a, b and c and alpha, beta and gamma. So, for the cubic you will find in generally most of the elementary material science books will state that a cubic crystal system is defined by putting a equals b equals c and alpha equals beta is equal to gamma is equal to 90 degrees. Similarly, tetragonal a equals b not equal to c, alpha equals beta is equal to gamma 90 degrees. Orthorhombic again all three angles 90 degrees, but a not equal to b not equal to c. So, the first three conventional cells that we have are being defined by such relationships, and similarly we can go down the list. Now, there is a very big problem in this kind of a definition. In fact, this is perhaps one of the biggest misconception that is present in very large number of books as well as publications, and this is what I call as a big misconception. And what is the misconception? That this is a incorrect definition, that axial relationships determine the crystal system, and as I said, given in innumerable sources including textbooks on material science. Now, how to look at this? That how do I define then the 7 crystal systems? The 7 crystal systems, the classification is decided by symmetry, and the relationships like axial and angular relationships for the conventional unit cells are the consequence. So, we in this course we will be going into symmetry in quite some depth, and with that we will try to understand what is the crystallographic basis for the crystal system, and then extend this, that in these crystal systems now we put the lattice points, and we put the lattice points according to what we had shown here, that we have 4 possibilities of putting the lattice points at corners, lattice points at corners and body centered, lattice points at corners and end centers, and lattice points at corners and centers of all the faces. If I put this and I have 7 crystal systems, I have 4 possibilities of putting the lattice points. Therefore, I should have 28 lattices, but you will note that we have in this list that I have, for cubic I have only 3, I do not have 4. In tetragonal I have only 2 lattices, primitive and body centered. Orthorhombic I have all 4 possibilities. Hexagonal only 1 primitive, rhombohedral 1 primitive, monoclinic I have 2, and triclinic I have only 1. If we add up all of this, this constitutes what is called are the 14 Bravais lattices, which are introduced in an undergraduate class in a material science course. So, you will notice, let us look at the cubic. I have simple, I have written oblique primitive. So, the words simple and primitive are one and the same, but conventionally in these Bravais lattices they are typically written as simple, otherwise primitive cubic would also do. I have body centered cubic, I have face centered cubic, but I do not have a base centered or an end centered cubic. In tetragonal I have only 2 primitive and body centered. So, first that I have crossed out does not mean that if I have cubic unit cell where I take a cube as the unit cell, then these relationships would have to be obeyed, but these are not the basis for it to be defined as a cubic unit cell. Now, let us take some examples now and try to understand this, that why I do not have an end centered cubic, which is as at this again why an end centered cubic is not there. An explanation is given in many of these publications and books, and most of the time one finds that the explanation is actually wrong. So, let us first look at what kind of an explanation that is given. So, let us take a end centered cubic cell. So, I have lattice points at the corners, and let me put the lattice point at 2 opposite faces, the top face and the bottom face. So, this and I have this is A. So, since it is cubic, A equals B equals C, and all the vectors are orthogonal to each other, that is alpha equals beta equals gamma equals 90 degrees. Now, let us construct in another unit cell next to it, adjacent to it. So, again I have lattice points at the corners of this same cell, and so this is a basically we have translated unit cell by the vector b. Now, in this I do a construction where I join the lattice points like this. So, in fact, this becomes a new or an alternate unit cell for the same lattice, where now I have lattice points only at the corners. So, it becomes a primitive unit cell. Now, as we had seen in an earlier lecture, that any lattice can have any number of cells, in fact, and there can be an infinite variety of primitive unit cells. So, let us look at the dimensions for this cell. So, this is now let us say this is A prime, this is B prime vector B prime, and this is C prime. You very clearly A prime equals B prime. However, C prime is not equal to C prime. In fact, if I want to put these vectors in terms of the parameters of the larger cubic cell, then A prime equals B prime equals basically half the face diagonal, and the length of the face diagonal will be A upon root 2, while C prime would be equal to C, the dimension for the cubic cell. And what about the corresponding angles? Alpha prime, which is the angle between B prime and C prime, and would be equal to beta prime, which is the angle between C prime and A prime, and then finally gamma prime, which is the angle between A prime and B prime. They will all be 90 degrees. So, now I have a cell which is that two dimensions are equal, one dimension is not, angles are still at 90 degrees. So, if I go back to my lattice, I would say, and this is what is stated in many books, that is why we do not have an end centered cell, because we can represent it as a simple tetragonal unit cell. A simple tetragonal unit cell would have A equals B not equal to C and angles being 90 degrees, and it is a primitive cell. So, we say that this is tetragonal. Simple tetragonal. Now, if this for the case, though this statement is correct, that end centered cubic cell will not be there, but the reason that it will not be there is not that we can represent it as simple tetragonal. So, let me just take one more example to further take a point. Let us take a face centered cubic unit cell this time. So, this we had started with end centered. Now, let us take a face centered cubic unit cell, or we call it as FCC. If I take this, and let me draw an adjacent unit cell as I had done in the previous case. So, lattice points at the corners, and lattice point in the center of all the faces. I will not draw all the lattice points, but let me draw this common face, the center of this face. Let me draw the top face in both the cells and bottom face, and I will leave that, otherwise the diagram gets cluttered. And let us do a joining in a similar way that I had joined earlier, which means that let me join this lattice point, this lattice point, this lattice point, this lattice point, this one, this one, this one, this one, this one, this one. So, now I had first, this is A, this is B, this is C. The new vectors for the unit cell becomes A prime, B prime and C prime. As before, I will have A prime equals B prime equals A upon root 2 and C prime equals C, and I will have alpha prime, I will have alpha prime equals beta prime equals gamma prime equals 90 degrees. So, I have orthogonal angles. Again, this should suggest to me that this should belong to the tetragonal crystal system, and this time if I were to look what is the lattice. So, in this case I have lattice points corners and I have a lattice point in the body centered position, which means that this should be body centered tetragonal. Symbol that is used is I, but I already have a cell which is face centered cubic. So, if it was just a question of using a smaller cell having less number of lattice points, which means then I should remove face centered cubic unit cell as well from this list and put it in tetragonal. And taking a third example, just to take the point home, in fact, in all cases, in all of these lattices, whether it is cubic or it is monoclinic or it is hexagonal, all the 14 Bravais lattices can be represented by some or the other primitive unit cell as well. So, an example of that, let us take an example of that. Let us look at this face centered cubic, lattice parameters all equal, all angles 90 degrees at this unit cell described by the vectors A, B and C. Now, I have drawn some of the lattice points here. I have drawn only two of the corner lattice points, I have left the others blank to avoid any confusion, but I have put all the 6 lattice points on the centers of all the 6 faces. Now, suppose I take this the lattice point at the origin from where I have drawn the vectors A, B and C. Now, I join from here 3 of the lattice points. So, I have joined by a vector A prime to this center face, I have joined this lattice point at the corner to the center of this left face, and I have joined lattice point from the corner to the center of the rear face. And you can very clearly see that all the 3 magnitudes of all the 3 vectors will be equal, and they will be equal to A upon root 2. So, in fact, the lattice parameter of the alternate unit cell that I am going to get out of this would be all the 3 vectors A prime, B prime, C prime will be equal, and they would their magnitude would be A upon root 2, where A is the lattice parameter for the original larger cell. And if I look at the angles, so here alpha between B and C, beta between C and A, gamma between A and B, all 90 degrees, alpha prime, beta prime, gamma prime, analogously alpha prime between B prime and C prime, beta prime between C prime and A prime, and gamma prime is A prime and B prime. All the 3 angles will be equal. It is very easy to calculate. You can find first the end points of the vectors, and it's a, since it's a Cartesian system for this particular class, the end point of let us say vector A would be A upon 2 comma A upon 2 comma 0. End point of vector B prime would be 0 along A, but it will have half along B. So, B by 2 again since a, b and c are equal, so it will be a by 2, a by 2. So, I have coordinates 0 comma a by 2 comma a by 2. Now, just take a dot product of these two vectors and you will find this angle is 60 degrees. In each case, in all combinations, all angles would turn out to be 60 degrees. If I just go back to this, I find that I am in the rhombohedral crystal system, where A equals B equal to C and the three angles are equal, but they are not equal to 90 degrees. And let me complete the cell. So, I get this rhombohedral unit cell. So, which means that I can also represent the face centered cubic unit cell as a simple rhombohedral, but that is not the case. So, it is does not belong, the face centered cubic unit cell does not, or the lattice does not belong to the simple rhombohedral lattice. So, where do we stand? So, I would say that this is something that we have not come across, but we have to through this course remove this misconception and also determine the correct basis for determining whether a lattice belongs to the cubic system, or it belongs to the rhombohedral, or it belongs to a tetragonal system, so on. The basis for that is symmetry. So, we will stop here and continue next time.